Hello, can you hear me? Cool. Still coming, cool. I hope you came to find out how cool is Helidon. You all are using it, right? Okay. And we will talk how we are switching from the reactive web server to the purely virtual thread-powered thread per request model. Okay, I don't have to do the Slido thing, right? It's room 11. It works like with all the others. I am a Helidon developer. I work there for a few years now. You can find me on the Twitter and Medium and GitHub and everyone else with the same handle. I also have the Mastodon account, but I just don't remember the handle because it's too complicated. And what we will talk about, we will introduce Helidon for those few of you who don't know it already. Then we will take a look at the problems we solve. We will reintroduce the virtual threads again for those who didn't heard about it yet. I hope you all did. What impact it has on the Helidon MP, we will explain what it is. Some obstacles you can run into from the user perspective. And if there is time at the end, we will take a look at some challenges we had during the development. So what is the Helidon? The Helidon is a microservice framework. We used to call it the set of libraries, but that's what every other microservice framework is, right? Those are simple libraries you use with your business code to run it directly without any application server around. You just have it as part of your application. You deploy it all together. It's from start. It's a web server built to play nice with the Kubernetes. It keeps the number of third-party dependencies as low as possible, so your Docker images are nice and small, and the supply chain attacks and those things are not so imminent, and you don't have to get so many approvals for the third-party dependencies when you use it in your app. You can choose your path with right flavor of Helidon. You can kind of choose what parts of it you will use. That's simply because we have flavors for performance. It's now in the Helidon 3, it's Helidon SE, which is pure reactive web server built on top of Netty. It has reactive streams APIs. It's really fast, but you have to be seasoned reactive programmer to actually be able to handle it correctly. And if you make a mistake, it can bite you really hard. Then we have Helidon MP, which is CDI runtime with all the annotations and dependency injection. You have a JAX RS in there. It's very easy to use. It's imperative, so you don't have to be really the good reactive programmer to handle it. But there is a price for it, right? Because we have to we are using the Helidon SE under the hood, so we have to adapt it for the imperative use, and there comes the performance price inevitably. And then there is a new thing which comes with Helidon 4, and we will get to it soon. Helidon is packaged as a really smart jar application containing only your business code, and then you have the library lib folder with all those libraries you use, even those which depends to Helidon. So you can have nicely layered Docker images that all the others microservice framework does that because obvious reasons. We do the J-Link images. We do them really nice because we support the JPMS modules from the start. Most of the Helidon contributors are actually Oracle employees, so we have to, right? And we do the ground native image again from the start for the Helidon MP and SE, because we are basically sitting in the same office with the GraalVM guys. So we have been making everything native image compatible from when the native image came. And all the options are easy to use with the containers, obviously, because we are the microservice framework. But what problems we solve? We solve the same problems like any other server. We solve the concurrency. That's the thing that we need to solve. So the users doesn't have to. We need to be able to handle a lot of requests concurrently. We need to be able to respond fast, and we have to do it in the way that we spend not that much CPU cycles, and also we have to save in memory. So it's always about the optimizing in the server. And also we need to somehow handle that from our server handlers. You have to be able to call some lengthy stuff, to call other services over the HTTP clients, or you have to call the database and wait for something. So there are obviously problems with blocking, and that stuff we will get there. And why is this optimization so important? Well, it's a microservice framework. So in the cloud age, your manager actually every month gets a build, and he sees how good developer you are immediately, right? If it's the price is too high, you either code it badly or you choose the wrong framework. That's why we are optimizing so aggressively now in the cloud age. And concurrency is expensive. That's the problem we need to solve. We obviously, with the Java until now, this used to be used threads per request model has been just way too expensive, because the JVM specification doesn't really say how the Java thread should be mapped to the operating thread. So nowadays, the Java threads are just wrappers around the operating system threads. And when you start the Java thread, you are actually starting a new operating system thread. There is a system call behind it. You need a few megabytes of memory for each kernel thread start. And this is a problem which we have been solving for years now with the threads pools, right? So we have a pool of threads, and we are using threads all over again, and we don't really need to start too many of them. That's one thing. The other thing is the context switching. The context switching, it's when you block your thread and it doesn't do anything, it's just waiting for something else. The CPU will offload this thread, and another thread which needs to work will be rescheduled instead. But with this comes a problem that you have to actually remove every data of the previous thread from your CPU core cache and replace it with the context data of the next thread in line. And when you are having more and more threads, comes more and more expensive, and your system is getting slower, and your server is getting slower. So we have to avoid it, or we want to avoid it, of course. What we have been doing for many years now, that we have been avoiding the blocking with asynchronous programming. We are trying to keep the thread busy as long as possible. So we are scheduling, instead of rescheduling the threads, we are scheduling the work in a way that the thread is working all the time. For that, when we need to wait for something, we actually need to call some other service and give it some method to have the callback, which will be called on its own thread when it will finish. So your thread gets immediately free to do other stuff, to serve another request in this in the web server, for example. With this, we have kind of ditched this natural back pressure we had with the blocking, because if you block, you are sure that the sender, the requester, the one who lent you the thread won't send you more data because he doesn't have the thread, so he cannot, right? With asynchronous programming, he has his thread back, so he can call us many more times and send us more data. And we now don't have any good machinery how to tell it, okay, stop sending the data because I'm getting overloaded. And if you get overloaded, you don't even have threads for actually calling the callbacks, right? For that, the reactive streams APIs came. And that's when we started to be really reactive. Reactive streams APIs, those are really famous. That's the API for actual orchestration of the callbacks. So we have a set of interfaces which defines the mechanism for the callbacks, how to handle the back pressure, how to cancel things from the upstream, and how to handle the errors and everything. This API is also in Java since Java 9. It's in the concurrent flow package, and it seems really easy to implement. It's really simple API actually. But there is not only the API, there is also a set of rules, and this set of rules, what those reactive streams have to conform to, are really strict, and there is a lot of them. It's really hard to actually implement it right. That's why if you try to implement it in IntelliJ or any other IDE, you usually get some kind of a warning. Oh, be careful, you are trying to implement something which can bite you. So for that, there are already a lot of implementations of, it's called reactive operators. Those are usually libraries which gives you mechanics how to use reactive streams properly without actually having to implement the reactive streams API yourself. There is a lot of them out there, like the famous RxJava from David Carnock. There are reactor operators in Spring, Akka streams, the service talk from Apple. It's really nice. That's from the used to be Netty people. We have in Helidon our own operators, but most of them were actually contributed by David Carnock from the RxJava 2, so don't worry. And Red Hat has Mutiny. That's kind of interesting. They have different model of chaining the operators, so it's kind of nice. Depends what you expect or want to get from your operators. But does it help that much? Well, this is how the operators look. I made it a little more scary than it actually is, but you have to be kind of a senior to do the reactive programming right, because the learning curve is really steep. And if you do a mistake, if you do only a small mistake, you will make your system really slow, and you will lose all the good things about the reactive programming. You will lose that performance. That's the reason why you use this terrible thing at the first start, right? And you very easily can actually break it way more. For example, in the web server, if you block the handler in some operator, you will actually block the event loop thread in Netty. And your server will become unresponsive really quickly. It's disastrous. So you have to be really careful, and you have to do it right. But yeah, this is the example of the Helidon SE. That's how we are doing with our operators, the reactive programming. So here is the reactive endpoint. It's REST and resource get, and when it's called, we call the REST client, which calls another service, and we want to get a JSON object from it, get out the status of that, and make it uppercase, and then send the response. You can see that in the the response is actually sent in the callback from the REST client, so it's being sent on the thread which is from the REST client, and our server thread is not being obstructed anyway. And then you have some error handlings and business logic and so on. So you can see how we would debug that, right? Back to the Helidon SE. It's built on top of Netty. It's a very famous library for asynchronous programming over the Java sockets. Helidon SE provides the reactive streams API on top of the Netty, which by itself doesn't have the reactive streams, but has asynchronous APIs. We provide the operators and those things, so you don't have to have too much third-party libraries. Our operators are compatible with the Java's completion stage, so you can actually really easily connect them to the other asynchronous APIs in Java with some quirks, because the completion stage does handle the null, the reactive streams doesn't, and it doesn't have the back pressure mechanism and so on. But it can be adapted really easily. We also have the other reactive features, so we can connect all together nicely. So we have the HTTP client, DB client, reactive messaging, and fault tolerance, and a lot of features. So the reactive programming is a trap. We are in it for many years now. Anyone who tried to explain his reactive code base to any junior programming, to any newbie, knows why it's a problem, right? And I won't even explain again all the issues we had with it. The debugging is a problem, obviously. The maintaining the reactive code is hard. Even if you wrote it and you get back to it in 2 years, you will be confused and it will take time. And there are some other issues, like offloading the abstracting code, the blocking, and so on. There is a solution. We have a virtual threads now. And it's been in a preview as a JEP 425 since Java 19, and now it's JEP 444 because it's been delivered. It's in the master branch of the OpenJDK for 12 days now, so the virtual threads will be part of Java 21. I don't know what would have to happen if they would want to roll it back, and I don't think it will ever happen. Hopefully, so somewhere in September 2023, we will have the virtual threads in Java. It's part of the project Loom, I will get there, which covers a lot of other things. It covers the virtual threads, the structured concurrency. We won't be talking about that in this talk. And some debugging support. There was a few days ago a question about if you can have a thread dump with the virtual threads. Yes and no, and that's why there is a debugging support part of the project Loom. I may get to it later. So this is my picture. We can block cheaply now. We can spin up the threads cheaply. It's very performant. The blocking is not a problem. No, it's not the green threads thing. A lot of people are asking that. The green threads have been in Java in times when Java was single-threaded. It was working on a single thread, and it was actually multiplexing the tasks on single physical thread. With one exception, on Solaris, there was a green thread implementation which worked in a many-to-many way, but that was simply because in those times the Solaris was running on the machines which had more CPUs, but the normal computers usually didn't have more than one, so it didn't make really much sense. This was replaced by operating system abstraction because it looked like a good idea then. We got into the point now when it's a performance issue for us nowadays. Virtual threads do it again in a many-to-many manner. So we have a pool of the carrier threads. Those are platform threads. And we are scheduling the fork join tasks in this fork join pool in a way that when some of it get blocked, it will yield and will be descheduled, and some other who is waiting in line will get on one of the on the threads in the fork join pool. So you can squeeze all the power from a course. What you are doing, you are actually using the same trick the reactive programming does. You are just hiding it behind the curtain. So you will have a nice code base, easy to maintain, easy to debug, but you will get all the performance for free. what it is, it's actually continuations in Java. So if you take a look inside the thread sleep method now, you can see there is a commit from a few days ago when it's been merged. And you can see that for the virtual threads, we are doing actually something different than the sleeping we used to do before. If you will follow the rabbit hole deeper inside the virtual thread class, you will find a method which is called yield continuation. And that's just give you the idea of what's happening, right? It's the continuation and implementation in Java. That's what we get. And we can now compare it with, we already saw this one. This is the reactive endpoint in Helidon SE. We have explained what this does. It does the uppercase from some object on different microservice and send the response from the JSON object. It handles errors and those things. And you have to understand the reactive streams to actually be able to work with it. This is what the Nima does. This is exactly the same thing. We are just getting imperative. We call the client, which is not reactive anymore. This is our own Nima client, but you can use whatever you want. You just block until you get the response. And when you get it, you have the status from the JSON object. You do the uppercase thing and send it back. And it performs in the same way as the reactive programming, just because we have used under the hood the same trick, the continuation. When we blocked the client and we have been waiting for the response, the physical thread was actually doing something else. So there was no context switching on the CPU core. There was the context switching only inside the JVM. So it's way easier to debug. You just place a breakpoint. The order of operations gets from up to down, so you don't have to actually set up your breakpoint somewhere in the operators and check which thread it's running on and what's the order of things and if it can be concurrent or not, and so on. When there is a problem, you just throw exception. You know, here you have to have completely different way how to manage the errors in reactive streams. Same result, same performance, but it's way easier to actually work with it. We all know this because this is how we have worked 15 years ago, right? Now we have a fresh release of, fresh alpha release of Helidon 4. It contains Nima. The Helidon MP is based on the Nima there. And it's also the last release which will contain the reactive web server. It will be completely removed, so in the final release of Helidon, there won't be any reactive web server. You will be running everything on top of Nima. New Alpha 6 requires JDK 20 for now, with enable preview, and when there will be final release after the release of Java 21, it will be obviously the minimal version for Helidon 4 will be the Java 21. With the virtual threads. We have, those are the features we have now in Nima. We have HTTP1 with pipelining, the server client, HTTP2 with TLS or without. We do all the upgrades. We have a server end client. We have gRPC prototype. We have a server. The client is to be done. We have a WebSockets prototype. It's also interesting. And we have made it extensible for other TCP protocols, so more goodies will come in the future. We have some great testing support and so on. A lot of features. With Nima, there will also come some new features into this Nima, not to the Helidon MP. So in Nima, you will actually optionally be able to use dependency injection, but the compile time one, so it will be super fast. It's not CDI, obviously, but you will get it. You can use your favorite annotations for everything, and it will be still super fast. We have builders now. It's a nice feature. It's inspired by Lombok, but it's more powerful. It does a lot of interesting things. Those things are really new, so there will be some articles coming out shortly. And we have a config beans now, which is again, it's it's compile time generated configuration objects, which you can then load the configuration with, and you don't have to ask for every configuration property one by one. What we have as a thread model? Well, there's a nice thing about Nima, because it's a thread per request model. So the server is actually really small. It's really simple. By removing the reactive web server from the Helidon, we are getting of so much stuff that is potential bug hidden somewhere, right? Because we are just using the Java sockets. There is no really clever magic in it, except that we had to kind of try all the approaches how to use sockets efficiently, but with the help of the Loom team, we came to some interestingly simply approaches how to use it. So now we have a physical threads which are actually listening on the sockets. Those are always one per opened port, and those are spinning the virtual threads per one or two of them per connection. So you have one for the reading and whether you have a direct writes enabled or not. That's a kind of a performance thingy, because it works. Those sockets performs a little differently on the Mac and on the Linux or on some different kernels. So you can tune it up to be even faster. The HTTP2 spins up new virtual thread per each stream. That's obvious, right? So again, the threads per request model. We are just spinning the virtual threads wherever we want, and it's super fast and super cheap. Yeah, now we will take a look at the comparison with a raw netty handler. I did this benchmark at Sunday for you with the latest alpha release. I will again say the netty is the famous library. It's been used by almost every other microservice framework or web server on the market, because it's very performant library for working with sockets asynchronously in Java. Performance is measured with Werker, like in the famous Techem benchmark framework. I have used just some of the tests, not all of them, because that would be like super hard to show all at once. And I did comparing in requests per second. So this is it. This is the Nima, the latest alpha version, and this is the netty 4.1.36, and here is 4.9.91. You can see that the netty got faster. They started to do a lot of optimizations lately. I hope that's because there are new players in the field, right? So it's always good for the users that if we are trying to overcome each other. The important message here is that we are almost on par with them. They are obviously optimizing for like 10, 15 years now, so okay, but we are really close. The thing is also that the netty handler is something nobody really uses in production, because using the netty raw or netty handler directly, you don't get the fully featured web server. You know, they don't handle everything for you. You have to do it yourself. While the Nima is full-blown web server, so it handles all the 100 continuous in HTTP protocol and so on. So we do more stuff, obviously, but we are pretty close. So you can see it's we didn't lose anything by using imperative with virtual threads. How is it possible? Again, we are avoiding the context switching. That's all the magic. That's a trick we are trying to do. That's a trick the reactive programming has been trying to do in Java for so many years, but without all the clutter around. And now we will take a look again at the Helidon MP. This is the handler of Helidon MP. It's imperative coding. You just using the annotation. It's JAX-RS. Everybody knows that. You have the full CDI dependency. We have a weld. We are using the weld for it in MP. And basically, you get all the good parts from the Jakarta EE. We are implementing the microprofile specifications. So that's kind of like a spin-off from the Jakarta, right? Yeah. We can see now that this is how it's been in Helidon 3. The MP was actually powered by the reactive web server. There is a performance penalty for that because you have to abstract away the reactive programming, and that's costly. But now, we have Nima, and it's just replaced the Helidon SE, the reactive one, under the hood in the Helidon MP. So Helidon MP immediately got power boost, like really nice one. And because we don't need it anymore, it just won't be in the Helidon 4 anymore. There won't be any reactive web server there. And does it fit? Well, it just fits so nicely. There is no complicated wiring anyhow. It's all imperative, so we just connect together the input streams and it works. It's just awesome. We have the back pressure just by blocking. We have the input streams. Those are cool again, right? This is just way, way better. This is the older comparison from Alpha 2. I didn't really measure it again, but this is what happened when we first time ran the Helidon MP on top of the Nima. We got like 4 times faster. It's just because we removed all the clutter under the hood, you know, the offloading to the physical threads, because with the MP, with the transition between the Helidon SE and MP, we had to actually offload all the work to the physical threads, and we did some thread pooling, but you know, it's costly. And we are not finished yet with all the optimization yet. There are the problems we don't solve. For example, you all heard about pinning the thread, so there is the synchronized block with some I/O operations in it and those things. Those are technical things which everyone can have problems with the virtual threads. That's the thing which is up to the Java team to solve. They are solving it. They have solved a lot of it already because the real magic is happening, you know, all those I/O interfaces in Java when they have to do the virtual thing, virtual thread yielding correctly and so on. The problem you as a user have to look at is actually the thread abstraction. That's when you are doing some CPU-intensive, long operation, like, I don't know, mining the bitcoins or something, right? So it takes time. It keeps your CPU running. So it will keep the carrier threads under the virtual threads actually still in operation and won't let it to be used by other virtual threads. The multiplexing won't work that nice. This will force the virtual threads to actually spin up new carrier threads to compensate. This compensation mechanism works for some pinning problem. It doesn't work for some other pinning problem. So to do the things like that, you have to be offloading. But what you would have to do with reactive programming, it's the same problem, really, because we are doing the same thing. We are just moving it behind the curtains. With reactive programming, you have to offload it to another thread. So in Helidon, we had this fault tolerance async stuff that you could actually run some task on different threads and wait for the responses synchronously. So this is what you would do in Helidon SE. You would offload it to the physical thread, and event loop thread in the web server wouldn't get obstructed and could actually handle another web server requests, and you wouldn't get stuck with the whole server just by calling the Bitcoin mining 4 times, right? Because you had 4 threads, so the event loop has 4 threads, and then you are done. Yeah, this is the Helidon MP on Helidon SE, so it's in Helidon 3. This is what you do. You don't have to do anything because it's all offloaded already. This is what we do, what we did, and that's why we had the performance disadvantage. And this is what you do in Nima. You do exactly the same thing. You just offload it, and you don't have to use callbacks anymore, right? Because the blocking works nicely. So we have, again, fault tolerance features. You can offload it to another thread, or you can just spin up a new physical thread for yourself. It works the same. And in Helidon MP on top of Nima, we have a notation for that. So this is actually a micro profile. It's part of the spec. So it will offload it for you on a physical thread, and you are safe. And that's about it. There was some interesting challenges we had during the Nima development. The funny thing was actually the performance tuning. We have to say thanks to Alex Kukchenko, who is a performance guy in the Loom team, and he helped us in one occasion by removing a lot of my code to make it faster. and they kind of they know how to look at things to make them work faster, right? And also the hardest part is actually learning how to block again, because if you work with reactive code for a long time, you kind of start doing this, avoiding the blocking subconsciously. So you see the get, you see the await, and then your mind starts spinning, okay, I need callback for this, and I need to connect it to this, and I need to handle errors and everything. And that kind of takes time to unlearn. Because in Nima, after the exercise like that, you just say, okay, I can block now, and just wait for what happened, right? The reusing the byte buffers, that's also interesting, because we were following this similar approach like the Netty does, that's avoiding the garbage collection. In our benchmarks, it turns out that garbage collector with virtual threads has been working actually more efficiently than when we have been trying to do the byte buffer reusing stuff. So we don't do it anymore. That's one of the things that Sergey removed. Asynchronous writes have been kind of weird thing, because the implementation of sockets in JDK differs depending on the operating system sometimes. So we have some configuration tweaks which you can actually do the direct writes. There was this TCP no delay thing, right? When you have this algorithm on the sockets, when you are sending the packets, you actually wait a second if the other comes and send them all together to make it more performant. But this works better for the request response protocols, and in HTTP2 it goes completely differently, and those things. So those are the interesting stuff we are solving every day now. The blocking, we have used the blocking sockets, not the asynchronous ones in the end, because they are just faster. It was kind of surprising for us, but it works way better this way. And again, relearning the blocking. HTTP2, that was fun. I don't know if anyone was trying to implement here HTTP2 by himself. It's a different protocol than HTTP1, and it comes with a lot of interesting challenges. But with virtual threads, you can have a lot of threads, so you don't have to do thread pooling and those things. So it gets a little nicer. It's definitely way simpler than the HTTP2 implementation in Netty, for sure. The gRPC that was on the other side, surprisingly simple. We just connect the things together. We didn't use Netty, obviously, but we connected to the Google APIs, and it all worked really quickly. And this slide is old, and I shouldn't have it there, because we did introduce much of the new stuff. So I'll just skip it. If you want to know more about Helidon, we have web pages, we have a Medium channel, and Twitter account, and YouTube channel when there are some videos we are trying to do. We have a Slack channel. This is actually free support from the community and from the Oracle employees, which is for free. So you get some support for free. Yeah, we do the free things in Oracle. I forgot to mention the Oracle is an open source, and we have also contributors from outside of the Oracle. So it's not only the Oracle workshop, but you can use it for free. You can fork it and change it and do it whatever you want with it. we are just hoping that we will make money on the OCI and the cloud thing we have, and when you are using Helidon there, because we are trying to integrate everything well with our other stuff also. So we have great connectors to work with WebLogic, JMS, and OCI streaming and those things. So if you are in the OCI, the Helidon will make things easier. And there are some, there's a link for a GitHub repo with the examples I have shown here, most of them. And on the Slack channel, there are also the outside contributors who can help. Usually we answer really quickly there. We also discovered that there is some community about this closure wrapper of Nima. So there is already a closure wrapper which is called Mina. And you can find it on GitHub, and it's really cool because we didn't even know it's happening, and then it came up. And I'm not really a closure guy. For me, it's like parallel on steroids or something. But some people are using that. That was interesting. So that's all from me. And we can move to the questions. Yeah, I will try to switch. How's the time? We have 8 minutes for the questions, right? Do I have it opened, right? Yeah, I see. So I can place a question. Cool. I guess I don't want to have it dark, right? That was a mistake. Okay. Is it better? Have you replaced the thread local? Yeah, thread local, transaction security. Well, the thread locals, they work with virtual threads. A lot of people are asking, they works. It's just the thing that you have to understand that the bigger the data you hide in the thread locals, the slower the thing will get. That's how it works. For that, there are those scoped values, part of the Loom. They are still a preview, I think, but we have in Helidon very similar feature already that's been there also for the reactive code is this Helidon context thing. So what the scope values does that you actually have a context, some lambda you run, and before the lambda it will set up the context, and after it will destroy it, and it's immutable, and exactly the same thing we already have in Helidon. So in Helidon you don't necessarily need to use it, but if you are using a library which are relying on the thread locals, it will work. It's just you have to kind of keep an eye on the size of the things, because you will get slower and slower, because obviously you will be scheduling all this stuff much harder when there are megabytes of things inside the thread locals. So it works. The another one is, what kind of blocking methods are allowed in order to virtual threads to work? Well, avoid the synchronized statement. Avoid the object wait, and then you will be basically okay. Because the reentrant locked works really well. It's just a synchronized. And with synchronized, it's not all the time. It doesn't really mean that if you use synchronized, everything will break. It's just constellations when inside the synchronized there is some I/O operation, and then it goes can go sour, and you can hit the case when the virtual threads carrier thread pool won't compensate for the pinned thread, and that can lead to problems. So avoid the synchronize wherever you can. The reentrant lock works the same. We have seen some codes where the synchronize have been used and everyone was afraid, and then we figure out that most of it is being actually eliminated anyway, so it didn't really matter. But it's better to avoid synchronize. You are that close to netted. Does that mean you are a lot faster than the other frameworks? We are faster than some, but there are frameworks, well, say it loud. There is, for example, Vertex. It's really well optimized. So with Vertex, we have some internal benchmarks, and we are really close, yes. We will place Nima into the tech and benchmark shortly, so you will see it for yourself. Which garbage collector you use for testing each site? Well, there is a performance team as part of the Loom team, which are doing those tests, and they are testing all of them, which works with virtual threads. So I don't know really particularities. We just get the memo when something goes wrong. That's why another virtual thread for writing the response? Because in some cases it's faster. Why another? Yeah, could adoption of Helidon 4 become a problem due to the Java 21 dependency? I don't get it. Well, problem? Well, is it a problem if you have Java 21?
Many customers won't upgrade to the latest.
Well, then they cannot use the Helidon 4. We are going all in with the Java 21. In Oracle, it's well, we can stay with the enable preview feature. We even have customers who want it so badly that they actually want to do it with the enable preview feature. Problem is with enable preview stuff that if you compile it with this version of Java and you use it in another version of Java, in the newer one, in Java 21, for example, your library won't even run. Because there is a hard check that, OK, it has been compiled with preview feature for the Java 20. So you cannot really load it with Java 21 anymore. So we have to. It have to be this way. So just, OK, we are hoping the whole world will switch to Java 21 as soon as possible. Will Helidon remain microprofile compatible in the future? When will it support micro? Oh, I am not really into it. I think we either already do or it's almost finished. I'm not really that familiar with it, but what I did implementations for LRA, for the messaging, and for the reactive operators, and those are not under the umbrella. So those are not part of the MP6, and those are done by other guys, so I don't know that much. But I think we are either close or we are already there. Does Helidon keep up to date tech empowered benchmark config? Is the benchmark reliable? Is any benchmark reliable? We have our own, OK. We can talk about this for a long time. There are frameworks there which are doing the really dirty stuff. We are trying not to be dirty. We want to be kind of like, OK, if someone looks in there and finds something dirty, he'll say, OK, the Helidon guys, you know, they are doing dirty things, so we cannot trust it. So we are trying to do it the right way, so we can show it to our managers. OK, we are that fast. They like those graphs, you know. So, are you planning to automate the upgrade or switch to Nima? In Helidon 3, in the SE version, with MP, it will be really easy, right? But with Helidon SE, in Helidon 3, we have designed our reactive API in a way that it's super similar to the Helidon Nima API. So it's been pre-designed in a way that the switch will be as easy as possible. So if you are using Helidon 3 and you are using the newest best APIs there, not the replicated ones, it should be really easy. You just won't be calling the response sent in another callback. You will call it directly when you are ready, and you can block. So it won't be that different. It's actually easy to switch, I guess, in most cases. Is it all? There was this question about the thread dumps, right? I heard it a few days ago. Can you see the virtual threads in the thread dump? No and yes. There is, as part of the Loom project, there is this debugging support. So if you are using the JCMD binary, you can do a thread dump with virtual threads. It's there. Well, in IntelliJ, you don't see them yet, but I guess it will get there eventually. With the Java flight recorder, there are switches with which you can actually turn on the events when the virtual thread is starting, when it's ending, when it's being pinned. That's really interesting when you are trying to debug the pinning problem. So There are debugging features, and a lot of them is on the way. That's just because it's really fresh thing. So yes, you can have a thread dump with virtual threads. It just won't be, I think, the one which you get from the IntelliJ now. I have stickers with Frank, the bird, if anyone wants it. All the users of Helidon.